Alright, so we ran a little short on time today, and I just thought I'd make a quick video to finish up the material for Chapter 15. So remember where we were? We were talking about standing waves on a string, and we had derived the expression for a standing wave, and we see it right here. And so remember that the amplitude of the standing wave is equal to 2 times the amplitude of the individual waves. So the way that we made the standing wave is we started with a sinusoidal wave that's traveling in one direction. It reflects off of a fixed barrier, so it inverts and then travels back in the other direction. And so this continually happens, so we have waves traveling both directions, but both of the waves are identical in terms of their wavelength and frequency. And so what happens is you set up what we call standing waves that exist on the length of the string. And this is a picture right here of what the standing wave might look like. And this is sort of, while this is sort of a time-lapsed or long time exposure of the string, we saw in the video when we looked at it, you also sort of see this pattern. And so I'm just outlining what I would think of as the envelope of the standing wave. And on this envelope we have antinodes, and that's where we see the largest displacement. And so the antinode would have an amplitude of the standing wave. And then we also have nodes. Now, this whole expression right here really describes the outline, which would be the red outline that I have in this picture. And so you notice that it depends on x. So the location of, where these nodes and antinodes take place have particular values of x, depending on what the value of the sign is at that particular value of x. And we can use that knowledge to figure out where our nodes and antinodes would occur. I just wanted to show you some other frequencies. What happens, the different types of standing waves that we see on a string is going to depend on the frequency of the wave. And as the frequency will increase, the pattern of the standing wave changes. And so these two examples are, the two nodes would be the second harmonic. This is the third harmonic, and this is the fourth harmonic. So going back to finding the nodes, again, this describes the outline of the standing wave. So we're looking at the locations where this whole thing is equal to 0, which can be reduced to the sign of kx being equal to 0. And then, of course, we think about what angles give a sine of 0. So we have 0 and pi and 2 pi and 3 pi, etc. And we can find the x values by dividing by k. But remembering that k is 2 pi over lambda, we can also write the x's in terms of the wavelength. And so we can sort of say that, the nodes are going to happen at certain locations according to the wavelength. But, I find that an easier way to look at is by looking at these pictures, because then we have to say, well, how do we figure out the frequency of the wave, the standing wave, etc. And I find it much easier to look at the pictures and sort of go from there. So we have some pictures of the different frequencies of waves that might be set up as a standing wave on our string. Our string has a length of L, and the first picture is called the fundamental frequency, and that's the simplest case. And then as we go up and sort of have different numbers of antinodes and nodes, we call the increasingly complicated patterns, like first we go to second harmonic, then we go to the third harmonic, etc. So let's just first of all look at the fundamental frequency, which is the simplest one. So at the fundamental, we can see that, hey, in this picture, when I look at it, if I just sort of trace this from here to here, this actually looks like half a wavelength. So the total length, in the total length of the string, I only have half a wavelength. And so this allows me to make a relationship between the wavelength of the wave that is the standing wave and the length of the string. So I know that lambda is 2 times the length of the string. Now in terms of the frequency of this wave, which I'll call f sub 1, would be the speed of the wave divided by lambda, which I could rewrite as v over 2L. Now I'm going to go to the second harmonic. And when I look at the outline here, if I trace it, the standing wave, I can see that an entire wavelength fits on that string. So the length of the string is equal to 1 wavelength. So that makes it a lot easier. The frequency of this wave, which I'm going to call f sub 2 because it's the second harmonic, is equal to v over lambda, which is also v over L. And then finally, let's just look at the third harmonic. And also another name for these are overtones. So the second harmonic is the first overtone and the third harmonic is the second overtone. So now when I look at this one, here I have a whole wavelength right here, and then I have another half. So in the length of the string, I have 3/2 wavelength, which means that the wavelength of this particular wave is 2/3 of the length. And so here, because frequency is velocity over wavelength, I get velocity times 3/2 divided by L. I didn't write that very pretty, but so you get a sense of how we can find that. And then finally, remembering that the velocity is something that's not going to change. When I create these different harmonics by driving or sending a wave of increasing frequency through the string, but because the speed of the ring, remember, is governed by the tension and the mass per unit length, those things aren't going to change. It's just the frequency that changes. The velocity stays the same. And then we can determine the wavelength by relating the pattern to the total length of the string, and then from that we can find the frequency. So I find this a lot easier. If we jump a little bit, we can see that they have these expressions, for instance, for the fundamental frequency, and then kind of go on to the overtones. But it actually is a lot easier if you just use the picture to figure out the wavelength and then go from there.